Yes. Okay. Tomorrow you have to get there tomorrow. So it was you. That's by K? Yes, by K. Vision. This is what Mike showed. Yes, Mike is showing something. Rendering. Yes. I'll talk to you more. Closer and closer.
Yes. Yes. Now we do capture everything. It's impossible. Yes. Yes.
Did you check the quality of this?
Yeah, it's very good. Yes. It catches the people moves in chairs and so on.
Okay.
There's a noise here that can capture a very
Impression here?
yeah, a high frequency noise.
There's the fan. There is a fan.
Maybe here it's this monitor. I think it's on, so something like that. And that's noise that I capture with this.
It's too sensitive.
Yeah, I have to take in my home.
Filter.
Yes.
Out.
I got the profile and no other sound, and I only the profile this noise. And
Digital sound process.
yes. Yes, exactly.
No.
todos. Vamos começar, apesar de ter faltado um pessoal, né? É o seguinte, só para relembrar, hoje a gente não vai ter 2 aulas de Geant 4, a gente vai ter só essa, e depois a plenária, que vai ser lá no Campo, que vai falar sobre isso durante o Inverno, tá? Depois nós pensando, entre essa aula e outra, vai dar outros avisos para vocês, tá bom? A aula de hoje, o Luciano vai falar sobre a parte da física, que está dentro do Geant 4, então todos os modelos, todas as interações que a gente conhece, tudo aquilo que vocês encontram nos livros, ele vai falar em que parte do Geant 4 está inserido e como você pode modificar, se por acaso a física mudar, a gente vai lá e modifica. E também sobre o Primary Generator, que é a parte do Geant 4, onde a gente dá a primeira informação sobre a partícula que a gente está gerando. Então, como que ele funciona, como é que você define, nesse programa a gente vai definir o tipo de partícula, o ângulo de incidência da partícula, de onde eu estou jogando ela, qual é a direção que ela está indo, tá? Então, isso tudo vai estar sendo detalhado na aula de hoje, tá bom? Dúvidas que vocês têm durante a aula, levantem a mão e perguntem. Se precisarem, eu traduzo, tá? Mas não deixe de fazer pergunta. Eu acho que a gente pode começar.
Okay. Thank you. So for today we have some leftover which I left yesterday, which was the primary generator lecture. So one of the other ingredients of any mandatory, it's mandatory for any jump force simulation, which is to define what's the particle that you showed as a primary state. Some of you already yesterday, you gave a look at the source code and you realized how you select the particle which is sent and how you set the energy. So I'm going a little bit more on these aspects. Well, the primary generator is usually the easiest part to do in a jump force simulation because it's pretty much standard, unless you have to do something more specific like shooting 2 particles from the same vertex or shoot a star from the same interaction vertex and so on. So if you want to shoot 1 particle at a time, that's very much fixed recipes. It's more or less always copy and paste. So that's why I said that it is the easiest part in a jump force simulation. So now we are talking about this V-user primary generator action, which is a mandatory class. Remember, G4V means that it is mandatory. And it is something which is called every time you have a new event. So again, you have an initialization in which you build the geometry and the physics. This is done before you shoot run beam on. So run beam on is what starts the run loop. And here you have event 1, event 2, and all the events that you have to generate. So and every time you go through a new event, you have to generate an initial status for it. So for each event, you have to say how does it start? So which particle it is, which energy, from which position, and so on. So at every new event, you pass through this interface of GV primary generator, and you generate the initial state. So as probably some of you realized yesterday, in the exercise B1, the primaries are not generated from a single point, but this was kind of a beam. This was a box, actually, with something inside, and the particles were shot uniformly on a surface. So you had some kind of, you don't have a point source in this case, but you have some kind of parallel beam which was impinging on a side of a volume. So this is something that has to be taken care in the primary generator action. So what you have to do here is to decide the starting point, the direction of the particle, the energy of the particle, the type of the particle, and possibly the polarization if it's a gamma. So this can be the same for all events, but also it can be different event by event. It depends really up to your simulation. So in some easy cases, you just are happy with a beam of monochromatic particles, so all of them have the same energy, all of them have the same direction, all of them have the same position. In some other cases, you want some kind of randomization, so that you want to have a more complex source than just a so-called pencil beam, which is an ideal beam. So I was saying, this is the method which must be implemented is called generate primaries in your class, and these are the mandate to create the initial state. So it is done through a GAN, through a primary generator. There are a few of them. There are basically two of them that are used. One is G4 particle GAN, and the other is G4 general particle source. So in order to shoot particles, you use one of these in your class. And I'm going to be a bit more concrete in a while. So the simplest generator is the G4 particle GAN, which is what is used in the examples that you have seen so far. So when you give /GAN blah blah blah, so you tried yesterday to give some commands like /GAN /energy, GAN direction, GAN particle, you are using the G4 particle GAN. So what it does, it shoots one particle of a given type in a given direction from a given point. And you have several set methods to select these things. So you can set particle energy, set particle momentum, set particle position. So you have all the methods to set the status that you want to generate. So as I said, the primary generator is the easy part because it's more or less always copy and paste. So if you take this thing, and it's more or less okay for every application. So I'm going to discuss it a little bit in detail. So this is your primary generator. So it's your concrete class deriving from G4V user primary generator action. So you have to write a class which is yours and which derives from G4V user primary generator. Here what you just do, in the constructor, you instantiate the GAN and you set the defaults. So the defaults in this case will be a gamma ray going into the Z direction, which is 0, 0, 1. It means the Z axis direction, and 6 MeV. So this is the default particle which is shot, which is a gamma going into the Z direction and 6 MeV energy. That's it. So this is the default defined in the constructor of the class. And then in the destructor of the class, you just clean up the particle GAN. So this is the initialization of the primary generator. Then you have the generate primaries. So this function is called every time you have a new event. So here, in this function, you have to do to define what's the primary that you want for that specific event. In this case, for instance, what I want to do is to sample a direction isotropic. So I don't want a beam which is going into a given direction, but I want that particles are shot in all directions with the same probability. So I want to have an isotropic source, like a radioactive decay, in which the particles are going in every direction with the same probability. So what I have to do, I have to select a different direction event by event. So in the event 1, there will be a given direction, event 2 will be another direction, in event 3 there will be another direction, and I have to sample this direction using random numbers. So to sample is a direction isotropically, you have to select the direction angles, theta and phi, and theta is such that cosine theta must be uniform in -1 and 1, and phi should be uniform between 0 and 2 pi. So to define an isotropic source, the angles should be selected in this way. So theta should be such that cos theta is uniform between -1 and 1, and phi should be such that it's uniform between 0 and pi. So this is what is done here. So G4 uniform rand is shooting a random number between 0 and 1. So what you do here is that you take a random number, you multiply by 2, and you subtract 1. So this is a random number between -1 and 1. And you say, okay, this is the cos theta. Then you select also the phi by shooting another random number. So you say that the phi is uniform between 0 and 2 pi. So you randomly sample the direction. Yep. So you have defined those angles. And okay, so you calculate the direction sine theta sine phi, sine theta cos phi, cos theta. You calculate the direction vector. And okay, set particle directions. You assign the direction to the primary generator. So the next event will be shot in this direction that you selected. You can do the same for the energy, for instance. This is a non-physical case. I'm just sampling an energy from a flat distribution between 0 and 6 MeV, which has no physical meaning, but that's just to show. So you select a random number, you multiply by 6 MeV, so that you get something which is uniform between 0 and 6 MeV, and you say, okay, the next event, give me this energy. And this will be different event by event, because we are sampling using random numbers. So that's it. At the end of the day, shoot event. This is okay. I'm through. Just use this event for the next. Just use this primary status for the next event. So that's as I said, the minimum which is required. Just a warning: when you give /gun /particle whatever, this is called before this. So if you select here a gamma ray, and here you change it to an electron, this will be the last one executed. So what you write in the generate primaries overrides whatever you give with /gun /particle. So this is the last which is called in the sequence. So this is what is actually taken. So if you select with /gun /particle, you should be taking care of not changing these things into the generate primaries. This is exactly what I was saying. You can also give most commands, most settings by command line, as you discovered yesterday. So many of you did try to do some changes in energy, particle, direction, and so on. The things that you cannot do in this way is to do randomization. So you can select a fixed energy, a fixed direction, but you cannot do something more fancy like selecting from an isotropic source. So in this case, if you use /gun /whatever, you have to keep those parameters fixed. Still, you can have many runs, and between the runs, you can change the settings. For instance, you just select muon positive, 10 MeV going into the negative Z direction, and you shot 100 events. Then you change. You change to a muon negative, then you change the position, the starting position, and you launch other 100 events. So you may have many runs which differ for the initial conditions. There is something, this is the G4 particle gun, which is usually okay for easy application, like the examples that you have seen. There is something more fancy, which is called the general particle source, which is let's say a nicer replacement for the particle gun, because it can do something more. So it can do some randomization for you by command line. It can do some, you can generate many particles from the same vertex. You can define independent position direction. You can sample a particle from a volume. For instance, you can do this thing. You have here a detector, and you have here a source, which is not a point-like source, but which is extended. And you can say, okay, you just select me a starting point within this volume. I don't want a fixed point, but I want a random point within a given volume. So the general particle source is allowing to do that. So to do sampling from an extended source, which is very useful, for instance, if you want to simulate radioactive contaminations. So you have some radioactivity which is in your sample, and the radioactivity is distributed into the sample. So there is not a single starting point, but the starting point will be different and it will be uniformly distributed into your source. So there are a lot of commands from the /GPS, /pos, which allow you to change the type of source. For instance, you want a point source, an extended source, a planar source. You can change the type, isotropic, blah, 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 angular distribution, energy distribution. So some of the things that you have to do manually with the G4 particle gun, like to define an isotropic direction, it is coming for free if you are using the general particle source. So this is more powerful, and you have to do less coding for that. So one of the exercises that it's in the task 2 will be just to try this sampling, and you need to do manually if you use the particle gun, and you need just a few command lines like that if you use the GPS. So I want you to try both things to see the difference of the two flavors of generators. So this is something that you can do out of the box with the Geant 4 particle source. So without any kind of coding, you can change the energy spectrum like a linear source or a black body source or distribute the source over a square, over a plane. You can do quite a lot of different games with just by using command line. So that's pretty much convenient, even if you have a complex configuration of primary status. So here in the section 2.7 of the Geant 4 manual, you will see all the details of the commands that you can use from the command line to select the various initial state concerning position, energy, and direction of the source. So that's it for the leftover which I had yesterday. There will be an exercise for that later on, which is task 2. Now I would like to say something more about the physics, which is the other mandatory ingredient of any Geant 4 simulation. So we are talking about this G4V user physics list. First question, why we need a physics list? So in principle, the physics is the physics. So you shouldn't be able to select a physics, because physics is one and it's what nature chose. But things are a bit more complicated, because we are not able to catch the entire physics. We do through modeling, and some models are good in some cases, some other models are good in some other cases. So there are many models which describe the physics. And the models are usually not applicable to the entire energy range, so you may have models that are more precise, less precise, better tailored to pions instead of kaons. So that's especially true for the hadronic physics, but also for the electromagnetic physics, it's still the case. On the other hand, you are dealing with computers. So sometimes you want to have a precise result and you want to spend more CPU time to get it. In other cases, you don't care about so much precision and you want to have a fast simulation. So it's also a trade-off between the computation speed and the detail that you want to get from the simulation. As I was mentioning the other day, you want to do a good job, but you don't want to overdo. So you don't want to waste time to reach a precision that you don't need. So that's part of the job of the physicist. So to define the optimal balance between the precision and the CPU time which is required to achieve this. So the general philosophy which is in place since the very beginning of Geant 4 is that you may have different models to describe the same process. So a process is like Compton scattering. So it's an interaction of the gamma ray. And you may have different models that describe the same process, and maybe they were developed by different theoreticians. One is better at low energy, one other is good at high energy. They have different approximation. So in principle, you may have different models that describe the same physics process. And another thing which is important in the philosophy of Geant 4 is that you decouple the cross section, which means how far a particle travels, so the sampling of the step S, if you remember my first lecture. So this is driven by the cross-section and the generation of the final state, which is what happens when you really have this interaction. So the cross-section is where, if you remember, and the final state generation is what. So what happens actually. So the Geant 4 way to implement a physics list is through the G4V user physics list. So it's a user class that must derive from this G4 user physics list. And it has three methods: construct particle, construct process, and set cuts. So in the first one, you have to define all the particles. In the second, you have to define all the processes. And in the third one, you have defined the cuts that you want for the simulation, which I'm going to say in a bit more of detail. So if you need an electron to be followed by the simulation, in principle, you should explicitly define that you want an electron or a gamma or whatever. Still, it's stupid if you have hadronic interaction, you have hundreds of hadrons and particles. So they are some constructors that they build or boson or lepton in one shot. So the philosophy of the physics list in Geant 4 changed a little bit since the beginning. So at the very beginning, the philosophy was, okay, you are the physicist. You know exactly which physics you want. That's entirely up to you to define which is the best model for your simulation. So this is the most flexible way, so you have the complete freedom of changing the physics, but this is complicated. I think not everybody here is able to distinguish between, I don't know, two kind of hadronic cascades at 100 GeV to say which is better for your simulation. So it's true that it's completely flexible, but the average physicist is not able often to assess all the models that you have in Geant 4 to say which is the best suited one for the simulation. So this ended up in what we call flat physics list, in which you really have to attach to the gamma I want this, then to the proton I want this, and this. So for each particle you have to specify the interaction that you want to be activated. And this ends up in very, very long physics list, in which you really have to define everything at the code level, so C++, particle by particle. This is still a possibility, of course. This is the maximum flexibility that you want to get. But this is not what it's advertised at the moment. So they invented something which is modular physics list. So you don't build the physics particle by particle, process by process, but you build with some blocks that are building blocks. So like you have a building block for electromagnetic physics, you have a building block for inelastic interaction of hadrons, you have a building block for decays, and you can mix those building blocks. For instance, you may have different versions of interactions for hadronic. For instance, let's say for hadronic interactions, they are mainly two models that you can take into account, the so-called Bertini and the so-called binary cascade. And for the high energy, this is for the low energy part. And for the high energy part, you can take the QGSP, which is quark gluon plasma, or the Fritjof, and you can do any matching of this. So this plus this, and so on. So you can mix and match the blocks, so to build something which is not as granular as in the first case, but it's still you have just a few blocks to be included. So Geant 4, another good message is that Geant 4 is already providing some blocks ready for the use that you can use in your physics list. So this is what is done in the examples. I'm going to show it in a while. But you still can build your own builders, so to use your blocks together with the ones provided by Geant 4. So in this case, if you have to write a G4V modular physics list, it's a buffer class in the middle in which you don't need any longer to define the particle and the process, but you only have to define the cuts. So this is a piece of physics list. Suppose that you want a modular physics list. So this is your list, which derives from G4V modular physics list, and you want to register those blocks. So I want this block for hadronic elastic. I want this block for hadronic inelastic. So I'm taking the Fritjof plus the Bertini. And they want this block for the electromagnetic. So you are defining the physics by blocks here, and you have those three blocks defined, and that's it. And since these classes, they all start with G4, 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 it means that they are classes provided by Geant 4. So you are using some blocks that are already provided by Geant 4, and you are just mixing them according to in order to build a physics list. You can do another way, but that's the same. So there is an even easier solution, which is instead of using blocks, Geant 4 is providing a few lists complete that are ready for the use. So you can do a long list in which you do particle by particle the processes. You can do a 3 lines list in which you define the blocks, or you can take a list which is ready for the use by Geant 4. So Geant 4, let's say you have a few general cases. So in some, if they are realistic, they contain all model of interest, and there are a few flavors of them. So you can really plug and play them. So you don't need even to write your class. You just take the physics list which is provided by Geant 4 and you register it to the RAM manager without writing any class for it. This is of course the easiest solution, provided that the list of Geant 4 really match what you need to do, which is often the case. So in principle, they could also be used as starting points, so you can take them and you just replace one of the blocks with another if you want to try. So they are made by, they are modular physics lists by themselves, so you can really change one block and replace it with maybe yours or another one. So if you want to use a physics list like, I don't know, this is a physics list provided by Geant 4, gsp_bar.hh. So you just set user initialization and you just set it to the RAM manager. So you don't need to write your class, you just feed the class which is provided by Geant 4 to it. And that's it. That's the easiest way to define a physics. There are a few of them, a few physics lists. If you just have a look at the directory source physics list in the Geant 4 installation, there is some manual for it. And usually one of those, it's okay. So the code, the first string, it's the model which is used at high energy. The second string is the model which is used at GV energy or so for the hadrons. And HP means that you are treating specially the low energy neutrons. So that's also a rule of thumb in order to assess which one you want. So just to summarize this thing, you have three kinds of physics lists. The old style, in which you have complete flexibility, but you really have to do everything by hand, putting all particles or processes one by one. It's still an option, it's very flexible, but this is not my choice, especially for new people. Then you have something in the middle, which is that you have blocks, and you construct a physics list made out of blocks. You don't go particle by particle, but you go block by block. And you can use either the blocks provided by Geant 4, or you can use your block, if it's the case. The third option, which is the easiest, it's the really plug and play, so use the lists that are provided by Geant 4, and there are a few of them. So there will be another exercises in which, let's say, the example that is provided as a modular physics list. And at some point, I ask you to change this modular physics list with one of those provided by Geant 4, and to have a try. So to change a local modular physics list with a Geant 4 physics list provided and ready for the use. So far, questions to now? Okay, so far I mentioned pretty much the cuts. And you remember in the first day, I say that the simulations that are performed in the most modern codes are so-called mixed simulation, in which you divide the interaction in hard and soft. The hard interactions are those that are considered explicitly one by one, and the soft simulation, you just take the average of all the small interaction along the path. So instead of considering an electron, which gives many ionization, in which you have one electron volt, one electron volt, one electron volt, you just take them all together as an average deposition along the stack, and you only consider the case in which the energy of the ionization electron, which is also called a delta ray, it's maybe 10 keV. So you don't take one by one these very low energy things, but you consider them as cumulative effect, and you consider explicitly only the case in which you have a lot of energy emitted by the ionization. And this is saving quite a lot of time. Still, you can play with this threshold. So this 10 keV could be 5, could be 1, and this has an effect on the CPU time. Because if you go lower in threshold, you generate more and more secondary, and you have to follow them. So if you go lower in threshold, your simulation is more precise, but of course it's take more time. On the other hand, if you want something very fast, you can raise the threshold, I don't know, to 1 MeV, so that you forget about all the electrons that are below 1 MeV, and you consider them as a cumulative effect. But of course, your simulation will be less precise. So that's one of the trade-offs that you have to take care of. And the best trade-off, it's really depending on your simulation. So the general way of Geant 4 is to divide the process in 3 parts, 3 actions, the so-called at rest, along step, and post step. The first one, at rest, is what happens to a particle when it is idle, so stopped. So this can be a decay, this can be a positron annihilation, this can be a capture. So this is what happens to a particle which is idle. The second action is the so-called along step. And this is this thing. So the cumulative effect of all the small things that happen along a track. So they are taken all together like a cumulative effect. The third action is the so-called post step, and this is the hard part. So what happens at the end of the step in which you have the interaction which is sampled. So all these small things that happen along the track are not simulated explicitly, you just take an average. While the hard things that happen at the end of the step, they are simulated explicitly, so they get another track which has to be traced later on. So the question that everybody asks is, how low in this threshold should I go? It's okay to have 10 kV, or should I take 1 kV? It really depends on your simulation. Again, it's still a point of balance. So you want to have a precise simulation, but you don't want to overdo, because otherwise you get slowed down pretty much by the simulation. For instance, if your detector is a big calorimeter and you want to know the energy which is in the calorimeter, you don't want to go with 1 micron steps. It's just a big thing. So why to follow things with the precision of 1 micron? It's just meaningless. If you have a tracking silicon device, which is 1 millimeter times 1 millimeter, you really want to have the micron precision in the tracking. So depending on your detector, on the observable that you want to get, the threshold is really driven by your requirements. So if you have a big calorimeter and you only care about the energy, total energy, what about why tracking things very precisely here, follow and shower in this thing? You just care about the total energy. In another detector, maybe you need to know how the energy is released, so you need to know the 3D map of the energy release. So in this case, you need a better precision in the tracking, because you are really doing a dose map of your particles. So the precision that you want to get is pretty much depending on your application, and this has an effect on the threshold that you have to set. Something which is important in Geant 4 is that the cuts are never tracking cuts. So once you created a secondary, this is followed until it gets to 0 energy. It's never killed in between. So once you generate it, it's followed. What you can do is to either create it or not according to the threshold. So the cuts are only production cuts, are never tracking cuts. So once the track is there, it's followed until it gets to 0 energy. What you can do is to decide whether to generate or not a track. So it's whether you want to follow this or not, you forget it. So this tracking cut is applied to electrons and gammas from ionization and Bremsstrahlung. Both of these processes, they have a cross-section such that very, very low energy emission is favored with respect to higher energy emission. So you really want to set a threshold in order to avoid to have too many low energy secondaries. Another important thing in Geant 4 is that the threshold here is not defined as energy threshold, but is defined as a distance threshold. So it means I'm following an electron here. Here there is an interaction. And Geant 4 would like to generate a track of a given energy E. What will be the range of this track? How far would it go? 0.5 millimeter, let's say on average. So my threshold is 1 millimeter. So this track is not generated. It's considered to be as soft. So the threshold is not an energy threshold, but it is a range threshold. I'm generating only the tracks that can go at least 1 millimeter far. So this has some advantage, which I'm going to say. So actually, this cut is going to set the precision of the 3D precision of your simulation. Let me try to specify. Let's say that you set a cut 1 millimeter. Then you have an electron here, which is traveling in a material. So here, you try to generate a 10 keV delta ray ionization electron that suppose it will travel 0.1 millimeter. So if it were generated, it will be moved up to here. Since the cut is 1 millimeter, this track is not generated. So you say that the 10 keV are not released here, but they are released here in the interaction point. So this track is not generated. And you just assign the energy to the starting point of the track. This means that you make a little mistake because the energy which is in reality released here, you assign to this point. So you make a mistake which is 0.9 millimeter of where the energy is. So in the reality it will be here. Since this is below the cut, the energy is attached to this point. So you make a mistake of where the energy is released. But the mistake is 1 millimeter scale. So this is setting how precise in the space you are with your simulation. So it means that this simulation will be accurate at the 1 millimeter scale. So if you look at the sub-millimeter scale, your simulation will be approximate because you are doing this game. So that instead of releasing the energy here, you put here because it's sub-threshold. It is clear? It is? Okay, so having a cut in range means that you are selecting which is the precision, the spatial precision of your simulation. So for a silicon tracking detector, you want to have something which is 1 micron. For a big calorimeter, you can be happy with 1 centimeter or so. Because this is the precision that you want to get. You don't care about knowing the energy in a big calorimeter like that with 1 centimeter precision. It's no sense. So, and you want to pay the price for having such precision when you don't need it. And another advantage, what Geant 4 does actually, is that you set 1 millimeter, then Geant 4 converts this into an energy threshold for all the materials. So 1 millimeter in lead is not as the same as 1 millimeter in argon. So the energies, they will be pretty much different. So this is why Geant 4 uses this approach of defining a range scale. Suppose that you have a cut in energy, and then you have a typical argon lead calorimeter. Now suppose that you set a cut which is 455 keV, which is 1.5 millimeter in argon. So here, the tracking in argon is okay, but you spend a lot of time to track useless showers in lead. The other way, if you try to fit your cuts to the lead, which is taking an higher cut, you completely suppress the information in liquid argon. So having an energy cut is not efficient when you have different, very different materials. So having something which is defined in range, you set 1.5 millimeters in range, and Geant 4 automatically converts it into a threshold for the materials. So 1.5 millimeter means 500 kV in liquid argon and 2 mV in lead. So you have a precise tracking in liquid argon, and you don't spend time in tracking useless showers in lead. If you have a look at the Geant 4 screen when you run a simulation, you will see a table. Probably some of you have realized that, as a table in which you have the conversion of the cut in range into energy for all materials that are defined. So probably some of you have seen that you have a list of all materials like NAE, and then you have the threshold, which is calculated for each material. The cut is 1 millimeter by default, and then this millimeter is converted into an energy threshold for all the materials that you're using in your geometry. You just can pay attention to that, and of course, if you have lead, this will be an higher threshold than liquid argon or sodium iodide. So the energy threshold is just, what you do is to define the space precision of the simulation, and Geant 4 takes care of calculating the energy thresholds accordingly. So this is done in the set cuts, in which you can fix this cut, 1 millimeter for instance. You can also do that, you select different cuts for different particles. So you select a different cut for electrons and a different cut for gammas. What you can also do is to define different cuts in different parts of your setup. You have Atlas, which has a big calorimeter and a small tracking. So what do? Do you set 1 micron and you spend ages to calculate the calorimeters, or you set 1 centimeter and you don't have precision for the silicon tracking? So here you can apply different cuts to different parts of your setup. So that for the tracking part, you have 1 micron, which is the required precision, and for the calorimeter, you have 1 centimeter or so. So this is going to optimize the performance, the physics performance of the simulation. So you apply a precise tracking where you need it, and not elsewhere. I'm going very fast on this. It's the physics processes. I'm not going into much details, but what I want to mention is that I said that the philosophy of Geant 4 is to have many models which are able to describe the same process. For instance, you take the Compton scattering, which is a gamma interaction, and we have 6 models in Geant 4, different models to describe the Compton scattering. One of them is Klein-Nishina, so what you find in the textbooks. So you find the cross-section from Klein-Nishina, and that's a model to describe the Compton scattering. You know that the Klein-Nishina formula, it works in the assumption that the electron is idle, so at rest, and not bound, which is a good approximation if you are about 1 MeV or so. So if you are doing a high energy experiment, this is a good approximation. If you have 10 MeV gamma, the electron, it's really at rest and not bound. But if you are doing a 50 keV experiment, this is not true, because 50 keV, it's comparable with the binding energy of the electron. So you cannot take that the electron is at rest and free. So the Klein-Nishina approximation is not good if you care about low energy things like 50 keV or 100 keV. So in this case, you need some more complicated models which takes into account the fact that the electrons are not unbounded, that they are not at rest. So these models are more complicated, they are slower, but they are better to define the low energy part of the process. So you want to use them if you care really about 50 keV or 100 keV. Or you care about the polarization of the photon. Since the Compton scattering, you may have a polarized photon, and then also the outgoing photon is polarized. So here you have kind of inventory of all the models that are available for the gammas. And of course, the more precise you want to go, the slower the model gets. So you pay precision with CPU time. And this is again up to you to decide if you want to spend time to be precise or not. This is exactly what I was mentioning for the cross section of the Klein-Mishina scattering. So this is 50 keV gammas on gold. So in 50 keV, it's really comparable to the binding energy in gold. So this is what you get from the textbooks. So the Klein-Mishina with a sharp Compton edge. While if you take into account the fact that the approximations of the electrons at rest, the blah 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 do not work, you get a profile which is done like that, in which you really smeared out the Compton edge. You don't have a sharp edge here, but you have a transition, which is due to the fact that the electron is carrying some momentum. And you have fluorescence peaks, so escape peaks of fluorescence X-rays. So if clearly this is more precise, either the blue or the black. If you are carrying about 50 keV gammas in gold. On the other hand, if your simulation is 10 MeV, all these three are the same because the approximation they hold, but just you spend more time in this case. So it's good to have the precision, but when you need it. If you don't need it, you're just wasting time to get some over-precise thing when you don't need. So that's just to say that there are two flavors of electromagnetic models. So the so-called standard that are tailored to the, let's say, high energy applications, let's say above 10 MeV, LHC, and so on. And they are a version of models which is called low energy, which is really tailored to below 1 MeV. So for medical application, space application, low background experiments. So depending on your application, you may want to use either the standard or the other. So the low energies, it's good to be used when you need to go at the keV scale, when you want to know the fluorescence X-rays, something like that. And you can afford the CPU time, which is of course more, you need more CPU time because those models are more precise but slower. The hadronic physics is much more complicated because you have many models that are often phenomenological in different energy ranges, and often they are not matching each other as an absolute scale. So you have transition between two models, and the transition is not matching. So you really have to smooth them out. So here that you don't have a good QED model, so you don't have textbooks calculation, you just have parametric or data-driven models, which should be taken as they are, and you can try to mix and match with the others. So most of the models are phenomenological. What I would like to mention explicitly is that in Geant 4 there is a set of models that is called HP, which is tailored to track low energy neutrons, which is very effective but very slow because the cross section they are read by a database. So if you try to install Geant 4 and to download the package, you will see that there is a big database which is, I don't know, 300 megabytes, which is neutron cross sections. So the biggest database which is in Geant 4 is this one, which is used for the precise tracking of neutrons below 20 MeV. So again, this is low. So it's up to you to decide whether you want to do this precise treatment of neutrons or you don't care about. So you just use the normal tracking. So this is kind of an inventory of hadronic models. So none of the models is able to cover the entire energy range. So you always have to do a mix and match. So if you want to cover the entire energy scale, you have to take something of this at high energy, then something of this at intermediate energy, then something of this at low energy. So you really have to mix several models in hadronic physics. And this is what the physics lists are for. So to doing some of this matching. And the different flavors of physics lists that you find in Geant 4 are really different combination of these things. This was what I wanted to say. So I uploaded 2 tasks, the 2 and 3. I think we have half an hour today, so most of you will go through the number 2. And tomorrow, I will take the full morning, so I have maybe 1 hour lecture, and then the rest will be exercises. So the 3 and 4 will be for tomorrow, basically. So the task number 2 is about the primary generator. You have a 2A and 2B. The 2A is with the G4 particle gun, and the 2B is with the general particle source. Basically, you have to do the same thing in the two cases, which is generate an isotropic source, but you will see that in the first case you need coding, and in the second case it will be just command line, /GPS, /whatever, so no coding at all. So it's doing the same thing with the two kind of generators. Any question? Please.
You said that we cannot kill tracks, something like that.
Geant4 does not kill track. You can do by hand. So once a track is created, Geant4 will follow it until it either gets out or if you can kill manually a track whenever you want. For instance, you are doing a dark matter experiment. You need recoils, nuclear recoils. So a neutron is interesting for you only if it's maybe about 1 MeV. Thermal neutrons, you don't care. So if you have a thermal neutrons, you kill it because it's not interesting for your simulation. So you can kill track by hand, but it must be your choice. Geant4 will not kill any track by default once it's created. But still, you can kill a track anytime. For instance, if it's a gamma going in the wrong direction, you just kill it. If it's a neutrino, you kill it. So it's part of your optimization of the code.